All right, guys. Um, I welcome you all to this week's problem solving session. So looks like everyone is busy for this week. Uh, all right, no problem. I will be recording this session and I will be sharing it in YouTube. So you can go through this recording about this week 9 contents that I have created. And if you have any doubts, you can come back and ask me next week. Okay. So with that note, let's get into the this week's problems. So in week 9 content of the course, we actually studied a lot of things about turbofan engines. In fact, it is not like the previous weeks that we studied. So it actually included a lot of what are the recent advancements in the aircraft engines, be it both commercial and military engines. Also, we also studied something like variable cycle engines. So that is upcoming engines, which is very that is I mean, so they are planning to replace all the aircraft engines with the variable cycle engines, uh, if they were successful in implementing that. And those are few advanced aircraft engines, and we saw hybrid engines, turbo electric propulsion and all sorts of that. And finally we saw turbofan engine with intercooler and regeneration. So these are few advanced cycles that we studied. um, Although this course is fully consists of advanced aero engine cycles, uh, but this week is more involved into the advancements currently that has been in the industry and also being used in the aircraft domain, right? So that is what we studied in the course about turbofan engines, recent advancements, and such uh, uh, yeah, similar topics. So what I'm going to do today is I'm going to solve one question. Although your week 9 questions doesn't have any numerical problems, uh, it's still, I thought I will solve one question, a numerical question, which would help you understand the turbofan engines better. Okay, so that's the point. That's the reason I'm going to solve a numerical again in this week. Mm. So I hope all the other questions in your assignments, I think you should be able to solve it. I mean, there is nothing to solve. You all are uh, you know multiple choice questions, and you should be able to answer it if you have gone through the lectures. So I'm not going to get into that. Uh, Again, if you have any doubts, you can come back and ask next week. I will be available again next week during this time. Okay. All right. This so today what we are going to see is we are going to see turbofan engine with the intercooler and regeneration. The numerical is going to be based on that. And what I'm going to do is we already solved one numerical in our lectures, and uh, but that problem is for sea level, or the ground condition of the engine. And now what we will solve is we'll solve for a flight condition with mark pointed. So that is what I'm going to do today. Let's get started. Let me check my recordings. All right. So we all know the turbofan engine with intercooler and regeneration. You all must have gone through the lectures. So what we have is it's just it's the same gear turbofan engine, but additionally we are having an intercooling section between uh, low pressure compressor and high pressure compressor, and also regeneration or reheating of the uh, gases uh, between high pressure compressor and the combustion chamber. So the reason to do is when you reheat the gases, or let's say when you heat the gases based on the exhaust gas, the amount of fuel that you need to add in the combustion chamber reduces. So that's the whole purpose of this regeneration. So when you're so it basically minimizes the fuel consumption. So that's the thing. And uh, so that is what regeneration does. And what is the reason to go with intercooler or intercooling, why we need to do intercooling. And so that is something you need to think about. This is also be discussed in the lectures, but you think about it, why we need to do the intercooler. And if you are still confused, you can come back and ask me in the next lecture. Okay. So basically, we do both intercooling and regeneration in a gear turbofan engine. Okay. Let's quickly look at the TS diagram. So in the TS diagram, again we have small minor changes in the TS diagram. So from 3 to 3C, you can see I am uh, cooling the core stream and heating the bypass stream. So that is what you see here from 3 to 3C. Uh, from 3 to 3C, you see that there is a reduction in temperature, and that heat is used to raise the temperature of the bypass stream from 2A to 10. Okay, so that is the intercooling effect. And from 3C, again there is a high pressure compressor, so 3 to 4 there is a uh, pressure increase and also temperature increase. And from 4 to 4H is the regeneration uh, heat exchanger. So regeneration and intercooling both are just heat exchangers. Okay, and that is why we use effectiveness as a parameter for this. Okay, so you must have gone through the numericals in the lecture. So we use effectiveness for both intercooling and also for regeneration. So the reason is these two are heat exchangers, and heat exchangers performance is actually quantified based on effectiveness. Okay. Um, all right. We have Krishna Kumar and Tushar joining today. Thanks, both of you. So, what I'm going through, so since you have joined late, I will just quickly summarize what I did till now. Um, so, uh, what I'm going to go through is today I'm going to solve a numerical on turbofan engines with intercooler and regeneration. And so I haven't gone through the numericals yet, but you must have gone through week 9 content, so you must have some idea about intercooler and regeneration. So basically here we have turbofan engines with intercooler and regeneration cycle, and the TS diagram corresponding to this is here. So the intercooling effect is from a low pressure compressor to high pressure compressor, and the regeneration is done between high pressure compressor and combustion chamber in order to reduce the fuel consumption. So basically you are trying to heat the gases which is exiting the high pressure compressor without adding fuel, but uh, getting some heat from the exhaust gas. So that is the regeneration does. So in this way you are minimizing the fuel consumption, and that is shown in from 4 to 4H. Okay, that is the reheat regeneration region. And while doing so, the exhaust gas also reduces temperature, which you see in 7 to 8. Okay, we'll come to that. Now from 4H you have combustion chamber, which is again increasing the temperature to a very high value, T5, uh, and T5 is the turbine entry temperature. And from there you have high pressure compressor, high pressure turbine, and the low pressure turbine. And then you have uh, again it's getting cooled because of the regeneration effect from 7 to 8. Okay, and from 8 to 9 you again have nozzle. Similarly in the bypass stream, if you see there is a from 10 to 11 you have nozzle, the bypass nozzle, which is again shown by this one. Okay, so this is the entire turbofan engine with intercooler and regeneration. Just a minor recap. Okay. um, Tushar is telling, but will the exam of this course, when will be the exam of this course? I'm a bit confused. It is 26th September or 26th October. So it should be 20. I'm not sure why you are telling 26, but it cannot be 26 September because the course hasn't ended, right? So the course contains 12 weeks. So only till 10 weeks it has been out. So it should be 26th October. Uh, or sometime in the October. So that is what uh, I think. Okay, sometimes in the second half of the October. Okay, all right. So yeah, so this is the today's problem. So the problem here that we have is again two-spool gear turbofan engine, and this problem with intercooling and regeneration we have already solved in the lectures. And here what we are going to do is we are doing it for the flight condition. So in lectures we solve for ground condition. Here we are going to use the flight condition. However, all the engine parameters are all same. Okay. So for example, you have now the engine is flying at altitude of 11,000 meters with a Mach 0.8, whose pressure and temperatures are given. Okay, and the fan pressure ratio is 1.65. Low pressure compressor pressure ratio is 4.6. High pressure compressor pressure ratio is 6.6. Bypass ratio is 12.5. Turbine inlet temperature is 1830 Kelvin, and you have pressure losses both in combustion chamber and tailpipe, and you have intercooler effectiveness, pressure loss, and regenerative effectiveness and pressure loss you have. You have fuel eating value, and also core engine mass flow rate is given, which is 36.8 kilograms per second. So these are the input parameters, and then you have efficiencies and losses. Let's just quickly get into the problem. So this is what we solved in the lectures for the sea level condition or for the ground condition with Mach 0. These are the parameters that we got. So let's now try to solve solve the same engine for the um, flight conditions. Okay, so a quick overview of what we are going to solve. So initially we have inlet. From there we can get P and pressure and temperature at the exit of the inlet, and we also have Mach number with which the engine flies. So we can use that to find P02 and T02. And then we have fan, whose pressure ratio we know. From there we can from there the flow goes into the low pressure compressor, whose pressure ratio also we know. Now the only thing is from fan the bypass stream enters the intercooler, and from low pressure compressor also the air stream enters the core stream enters the intercooler. Now there is a heat exchange between the core stream and the bypass stream. It doesn't necessarily get mixed up. Okay, so these are two different pipes, so it's a heat exchanger. So um, and the core stream comes out as a core stream but with a different temperature because of the exchange in heat. Okay, so it comes out with P03C and T03C, and with which it enters the high pressure compressor. And at high pressure compressor we know the pressure ratio, so from there you can find pressure and temperature at the exit of the compressor. Now once you find the pressure and temperature, it doesn't directly get into the combustion chamber. Now it goes through the regenerator, so the flow goes near the exhaust gas. It gets some heat from the exhaust gas, and then it comes out. So there is a regenerator component, which is again nothing but a heat exchanger near the exhaust. So you can see this part over here is the regenerator, and from there you get the temperature would be a little bit higher, but the pressure would be a little bit lower because there is a pressure loss. Okay, and then it enters the combustor, where we add fuel, we reach a very high temperature of 1830 Kelvin, and then you have high pressure turbine which runs the high pressure compressor, and whose output core, whose air stream or gas stream comes out and enters the low pressure turbine, which runs both low pressure compressor and the fan. Okay, that's the configuration here. Now after low pressure turbine, the gases which goes out, it goes through the regenerator, and reduces it exchanges some heat with the inlet stream, and then the T08 would be lower than the T07. Okay, and this enters the nozzle, and from nozzle you can find velocity, pressure, and temperature. And then in the bypass stream, if you see, the bypass stream already went into the intercooler, and it comes out with a little bit higher temperature, which again enters the fan nozzle, and it gives pressure, temperature, and velocity, from which you can find thrust, TSFC, and other performance parameters like efficiency. Okay, so this is the overall idea. um, let's start with the first component. So I hope everything is clear as of now. If you have any doubts, you can always stop me at any time and you can ask. Okay. All right, so in the right hand side of this slide, I've given the so the, I've just copy pasted all those calculations that we did in the lectures. just for a give a comparison, but you cannot actually compare these two. These two are at two different conditions. That's it. So this is at ground condition, and this is at the flight condition. uh, there is no change in the cycle parameters. That is it. So this is just for an understanding that I have added it. Okay. um, yeah, so first we have inlet, and we all know how to find the pressure. It is coming from the diffuser efficiency and also isentropic flow relations. There is no change in the formula. You know, like each component has its own formula, and that there is no change in that. It depends upon your gas turbine engine configuration. Based on that, you may need to uh, you know calculate it appropriately. Okay. So that is the thing. So we all know this formula, so I'm not going to explain any of this. So if you just substitute these numbers in this formula, here the diffuser efficiency is 0.9 and Mach number is zero point 0.8. So if you substitute these numbers, you will end up having pressure to be 36.21 kilopascal. Okay. um, in the ground condition, since its velocity is 0, you are getting 1 bar, same as whatever inlet is, but here we are moving, and also the ambient pressure is lesser, so that's why you see 36.21 kilopascal as a pressure at the exit of the inlet. Okay. And then we know it's an inlet is a adiabatic process, so from isentropic flow relations, again you can get this. Here your temperature would be 248.16. Okay. And then we have fan. Fan is present, so it's the process from 2 to 2A. So there is some change in the station numbering here. Okay, that's something you need to note. So we know the pressure ratio to be 1.65. So from there you can find uh, pressure at the exit of the fan, which will be 59.75 kilopascal. So this will be, of course, will be different because inlet pressures for the fan is different in both ground condition and the flight condition. And then we have temperature ratio we can find based on the efficiency, isentropic efficiency, and if you substitute these numbers, you will end up having 1.1748. Okay, so uh, here your temperature would be something like 291.54 Kelvin. So please check whether these numbers are right. Uh, so there might be some algebraic mistakes. So I have tried my level best to minimize those mistakes. But if there is anything, if you spot out anything, please let me know, and I will appropriately change it. All right. So this is the component fan, and then after fan we have low pressure compressor. In the low pressure compressor, again we know the pressure ratio. So from pressure ratio we can find the uh, pressure at the exit of the low pressure compressor, and also we can find, based on the asentropic efficiency of the compressor, we can find temperature at the exit of the low pressure compressor. So this the pressure at the exit of the low pressure compressor is coming out to be around 242.65 kilopascal. Okay. And the temperature, again we have compressor efficiency, isentropic efficiency, which is 87 percentage. Although these numbers are not different between these two engines, basically these two engines are same, only flying at different altitudes. Okay. And hence the ratios will be same, but absolute numbers would be different. That is the difference between these two. So if you substitute these numbers, you will end up having temperature at the exit of the low pressure compressor to be 457.36 Kelvin. Okay. And now uh, the next component that we have is intercooler. So here is what you should be a little bit careful. Okay. Now uh, the core stream and bypass stream entering the intercooler we know. Okay. But what we don't know is the both core stream and bypass stream leaving the intercooler we don't know. And instead what we know is we know intercooler effectiveness. Okay. So I hope everyone knows this effectiveness concept. um, probably if you're a mechanical engineer or aerospace engineer, you should have studied about heat exchanger at some point in your bachelor's, maybe in first year, second years, or third years. You should have studied heat transfer, and if you would have studied heat transfer, you would have known heat exchangers. And in heat exchangers, we quantify the performance of a heat exchanger using effectiveness. Okay, and intercooler and regenerator are nothing but heat exchangers. And why we call it heat exchangers? Because the there is a exchange of heat between a core stream and the bypass stream. Okay, so that is the reason. So these two streams are at different temperatures, and we are putting it in a chamber such that uh, it can exchange only heat. It does not exchange mass. There is no mixing happening inside an intercooler, but only thing is it exchanges heat. So there will be a pipe, and on top of it there will be another pipe. So there will be a hot stream going inside another pipe, and then there will be that pipe might be made of highly conductive materials like copper or something, and hence it will allow heat to transfer from hot stream to the cold stream. Okay, so that is what is happening in the intercooler. And if you want to know the effectiveness of this any heat exchanger for this matter, the effectiveness is actually calculated based on, if you look at it, is the actual heat transfer by uh, maximum heat transfer that you can get from the heat exchanger. So you will ask me, how do you find actual heat transfer, right? So actual heat transfer is nothing but we can find, which is m dot cp into T exit minus T in for any stream, right? So that is what you see in the numerator. So T03C minus T03 is the uh, temperature difference in the core stream multiplied by m dot into Cp. Uh, Here in this case is just Cp into the T03 minus T03C divided by uh, what you have is maximum heat transfer that can happen is when the hot stream uh, gets out at uh, the temperature of cold stream inlet. Okay, please note that. Uh, if you have already known effectiveness, you would have understood by now. But if you don't know effectiveness, it's nothing but actual heat transfer by the maximum heat transfer, and the maximum heat transfer is nothing but, so there is a hot stream entering, there is a cold stream entering. So when the hot stream enters and leaves, so let me try to draw it here. So if I want to draw here, so this will be at higher temperature. Let's say these are temperature. This is T hot and this is T cold. Okay, so there is one stream which is entering. This is a cold stream entering, and then there is a hot stream entering. So it enters at opposite directions, let's say, for example. And here, when the hot stream enters, so what is the temperature with which it leaves? Yes, so it obviously some temperature will reduce. Okay, and similarly for the cold stream, the temperature will rise. This is how it goes. Okay, so then you can probably like TH in, and then this will be TH out. This will be TC in, and this will be TC out. Okay, so now when does maximum heat transfer happens is when your hot stream which enters at TH in, if it leaves at TC in instead of TH out. So if it reduces its temperature equal to the cold stream inlet, then that is when you will have maximum. So your hot stream cannot go below than your cold stream temperature, right? Because that is not thermodynamically possible. It can only go till cold stream temperature. If it becomes equilibrium, it can go till the lowest temperature which is present in the device. So here that lowest temperature is TC in, right? So the maximum heat transfer can happen when the highest temperature here is again TH in. So maximum heat transfer will happen when TH in reduces to TC in. So that is what you see here. Here the TH in will be T03. T03 is nothing but low pressure compressor exit. Okay, and TC in is T02A, which is fan exit within the bypass stream. Okay, so that is what you see in the denominator. This is the maximum heat you can transfer. This is the actual heat transfer. Actual heat transfer would be from TH in, it reduces to TH out. So actual heat transfer would be TH out minus TH in. You can also write it as TC in minus TC out. Both are same. You can, however you can write. This is also equivalent to, so what I'm trying to say is, this is also equivalent to T01 minus T02A divided by T03 minus T02. Okay, so these two equations are interchangeable. You can actually write it. But only thing is, denominator should be a maximum heat transfer. So this is something I thought I will explain so that people who are not directly from the mechanical background will be able to understand this. So if you have any questions, you can again stop me. I hope this is clear. How does this effectiveness formula came? Okay, it's nothing but actual heat transfer by maximum heat transfer. So now that we have know the uh, you know effectiveness formula, what we can just substitute. Nevertheless, we have already provided in the lectures, so it should be straightforward for you. So now you can just rearrange this. Effectiveness is already given. It's 90% effectiveness or 0.9 effectiveness here. So if you substitute these numbers over here, um, you will end up having the intercooler T03, which means the core stream which is getting cooled down is, it cools down to 298.55 Kelvin. So it actually enters at 457.36 Kelvin, and then it cools down to 298.55 Kelvin. So it's around like 150 160 Kelvin difference. Okay, so that is the so that's the operation of intercooler. And also they we also need to find pressure, because during in the intercooler we have some pressure loss. So this we all know how to find. So it's just pressure multiplied by 2% pressure loss, means you just multiply it by 98% of the inlet pressure. And if you do that, you will end up having 237.8 kilopascal. Okay, so the one thing you have found, so what is the temperature with which the core stream exits the intercooler, we have found using the effectiveness. Now we also need to find what is the temperature with which the bypass stream exits the intercooler, because that information is required in order to solve the nozzle. So after intercooler we have fan nozzle, right? In order to solve that fan nozzle, we need pressure and temperature for the inlet of the fan nozzle. So that should be coming out from the intercooler. So this is the change in the calculations compared to normal gear turbofan engine to uh, intercooler and regenerative turbofan engine. This is one change in the calculation. Okay, so as I said, we need to do for bypass stream. So for bypass stream, again as I if you remember, I wrote two formulas for effectiveness. You can either use that formula, that is also useful to find T0. So we need to find T010, right? And also P010. P010 is coming from the pressure loss. You can easily find 2% pressure loss. If you put, you will end up having the pressure, but the temperature which exits will be from, you can either use effectiveness or you can just simply use energy balance. So whatever energy is lost by the core stream is the energy gained by the bypass stream. So that is what we wrote here. So beta into m dot core into H010 minus H02A is equal to m dot core into H03 minus H03C. Okay. So m dot core goes away, and you will end up having uh, this kind of formula. And then if you substitute these, if this is not different compared to whatever, so these two formulas are same, there is no difference, only thing numbers are different. uh, and you will see that the temperature has increased from 280.9 Kelvin to 293.6 Kelvin. Okay, so there is something like 13 to 14 Kelvin difference. um, that is because the bypass ratio is 12.5. Mass flow rate is very high compared to the uh, mass flow rate in the core stream. So the core stream has to change to a very lot in order to give this 13 Kelvin difference in the bypass flow. Okay, so that is something, think about it how it happens. But energy as a whole also includes m dot, right? So that is the reason you see small temperature rise in the bypass stream, but a very high temperature drop in the core stream. Okay, and also we have intercooler exit pressure. Again, as I said, 2% loss, so 98% of the P02A will be 51.7 kilopascal at the exit of the intercooler. Okay. All right. Then what we have is, after intercooler and after in the core stream, what we have is we have high pressure compressor, and after high pressure compressor we have regenerator. So that is another trickier part. So let's quickly go through the high pressure compressor. We already know the pressure ratio, so it is straightforward to calculate the pressure at the exit of the compressor, which will be 6.6 times the inlet, which is 237.8 kilopascal. So the exit will be something like 15.69 bars. Okay, and we have temperature ratios, and you can substitute these numbers, and you will end up having you will end up having temperature at the exit of the compressor to be 543.76 kelvins. Okay. Now this this air with 543.76 Kelvin and with a pressure of 15.69 bar, it does not directly enter the combustion chamber. Instead, it goes to the regenerator, gets heated up a little bit to 4H, okay, and then it enters the combustion chamber. So that is the change. So that part we need to be a little bit careful. Okay, so in the regenerator for the core stream, it enters the regenerator at as I said, 543.76 Kelvin and 15.69 bars, and it exits with a pressure. So regenerator has a 2% pressure loss. So let's find out what is the pressure. It will be 98% times this. So the pressure at the exit of the regenerator for the core stream is 15.38 bar. Okay. Now we also need to find temperature. So how do we find temperature? We have regenerator effectiveness. As I said, your effectiveness here also is nothing but so it would be a good idea to write it down here. So effectiveness is nothing but actual heat transfer. So Q actual divided by Q maximum. Okay, and the Q actual would be what would be Q actual? It will be m dot core. So you can either select the course, you can either select the high pressure compressor exit air, or you can select the exhaust gas. So here I'm selecting high pressure compressor exit. So where it has to go through, it gets heated up from T04 to T04H. So it will be T04H minus T04. This is the actual heat transfer divided by the maximum heat transfer that it can happen is, it's nothing but again m dot is same, m dot core CPH. The hot stream has to reduce uh, uh, from T07 is the exit of the hot stream. Okay, T07, it has to reduce to the inlet of the cold stream, here where the cold stream is T04. Okay, so that's why you should write this as T04. Now m dot core and CPC is same, so you cancel this out, and that is it. You will end up having uh, the regenerator effectiveness. Okay, so this is how you calculate the effectiveness of the regenerator, and this is the equation that we have here. So let's go forward. Yeah, so this is one of the this is, so if you rearrange, we are interested in getting T04H. So in the T04H, so you will be asking, so you should be able to find T04H, but ideally what happened here was T07 we don't know, because T07 we need, right? So you can see here in the Q maximum is T07 and T04. And by the way, you guys didn't notice something. So here what I did is I just directly subtracted, I mean I directly striked out CPC and CPH, but here CPC and CPH are different, right? So actually what happens is, this is nothing but CPC. Okay, I will tell you the reason. So the Q max that we write here is nothing but C min times TH in minus TC in. Okay, this is the maximum heat transfer you are telling. You're not worried about which stream is going through that heat transfer. Okay, so the C min here is CPC. Okay, that's why you have this thing. This C min here is nothing but m dot core CPC. CPC, m dot core CPC is the lowest heat capacity. CPC is a specific heat capacity. C min is a specific just heat capacity. Okay, so C min is nothing but m dot core into CPC in this problem. Okay, you can do the same thing for the intercooler also, and you can see that, you can see for yourself how you are getting the effectiveness thing. Okay, so coming back, this TH in here is nothing but T07, and T07 we will not, we cannot know at this point of time because it's coming from the exhaust, it's coming from the outlet of the low pressure turbine. So we don't know how to solve this equation. So that is one problem. Okay, so now let's say, let me find out T07 because we need to find T04H, right? So if I want to find out T07, what I should do, I should look at, you can see the T07 is nothing but the exit of the low pressure turbine. So let's say if I solve for low pressure turbine, I will be able to get T07. So what does low pressure turbine does here? If you do a work balance, the low pressure turbine actually runs the low pressure compressor and the fan. Okay, where fan is connected using through a gearbox. Okay, so if you do this energy balance, the work generated by the low pressure turbine is nothing but is equal to low pressure compressor plus the work required by the low pressure compressor plus work required by the fan. If you substitute, if you put out the formulas, this is what you will get. Okay, so you should be a little bit careful. Here we have m dot core into 1 plus f into CPH, because in the combustion chamber we will add fuel and then it gets expanded in the high pressure turbine and then it gets expands in the low pressure turbine. So that's why you have 1 plus f CPH T06 minus T07. That is the work generated by the low pressure turbine, which will be equal to this is the work required by the low pressure compressor and this is the work required by the fan. Okay, this we know, we are doing this for last 6-7 weeks, so this is should be straightforward for you. So I can drop the m dot core here and I can rearrange and I will get T07. I can find T07, but again there is a problem. What is f? We haven't find out f, and also we haven't find out what is T06, what is the exit temperature of the high pressure turbine. Those two things we didn't find out. So then the natural instinct that you will have is, let's go and find out what is T06 and f in order to find the other two temperatures, right? So how do you find T06? That is nothing but the exit of the high pressure turbine. And what high pressure turbine does high pressure turbine runs the high pressure compressor. So let's say if I do energy balance for this high pressure turbine, then will I be able to get the T06? So if you substitute the formulas for this high pressure turbine work balance, so here you have in your left hand side you have work generated by the high pressure turbine. Again you have 1 plus f, which we don't know. And then you have T05. T05 we know, that is turbine entry temperature, which is given in the question, right? And T06 is what we are planning to find out. And then T04 and T03C we already found out till now. So only thing we don't know is T04H. Up to T04H we have found everything. So that is when we started going, in a reverse manner. So again, for T06, you will get this relation, but again, you don't know F, right? So how do we find F? F is in the combustion chamber. So in combustion chamber only we are adding fuel. So let's try to, do energy balance in the combustion chamber. So in the combustion chamber, from the exit of the regenerator, with some temperature T04H, we don't know that yet. The exact number we don't know, but it comes out at T04H. That is what we know, and that stream, will have some energy, which is this m dot core CPC T04H, and on top of it, we are adding some energy through fuel, which is m dot F QR eta B. We also have burner efficiency. So this will be equal to m dot core plus m dot F into CPH time T05. T05 is the turbine entry temperature, so which we know. So this we can rearrange it, and we can have relation for F. So now we got F, but the problem is we need T04H. So actually it's a loop. So to find T04H, we need T07. To find T07, we need T06. To find T06, we need F. And to find F, we need T04H. Okay. So, so it becomes a loop. So what we are going to do is, so we have these four equations. So these four equations we need to solve. So how many unknowns we have? We have four unknowns: T04H, T07, T06, and F. These four unknowns we need to find out. And how many equations we have? We have four equations. So system is actually closed. You can actually substitute these equations again and again, and then you can directly find the value. Okay, but doing this will be a very big algebraic process, and it will be really difficult. So what we do is we did iterations in the lectures, right? So that we manually did it in hand, all the iterations. So which I know you must have gone through, so I don't want to do that again. So instead what I did is I'm providing you a simple MATLAB code that I wrote, which does the same thing what we did manually, but here it is the program. So if we just run this, you will it will do the iteration by itself, and until there is no much change in the fuel air ratio, it will continue the iteration. When there is no change in the fuel air ratio, it exits and it shows me the final values of F, T04H, T06, and T07. Okay, so when you run this program in MATLAB, you can get this. This program is very simple, fairly simple. I think you can understand. I'm just putting it in a while loop. You can see, and I just coded these four equations, and I'm just checking whether there is any change in the fuel air ratio while doing so. Okay, once it converges, there won't be any change in any of these parameters, and then you no need to continue the iterations. You can take that as a final value. Okay, so that is what I did here. It's a straightforward thing you can go through. So finally we got all these four values together, and your fuel air ratio was 0.0275, and T04H is 1009 Kelvin, and T06 is 1620 Kelvin, and T07 is 1091.86 Kelvin. Okay, so we will see what these numbers really mean. Okay, now only thing is, now let's go forward. Since we found T04H, we can use that T04H, which is 1009.465 Kelvin. So that I wrote here. So you can do this combustor. So we know there is a pressure loss of 3% in the combustor. So if you do this, you will end up having 14.9 bar at the exit of the combustor. On top of it, again, you can do energy balance, but we don't really need to do this energy balance because we already know the fuel air ratio. So fuel air ratio is nothing but 0.0275. Just for the sake of completeness, I have given the formulas also here. Okay. So this fuel air ratio we already found during the iterations from MATLAB. Okay. Now, when you go forward, the next component that you have is high pressure turbine. again, we already know the energy balance, so we no need to really find the exit temperature. But for the sake of completeness, I have given the equations here. So if you substitute these numbers again, you are going to end up having 1620.43 Kelvin at the exit of the turbine. So it enters at 1830 Kelvin, and it leaves at 1620 Kelvin. So one thing that we can see is, let me go back a bit. So at the combustor, the inlet is 1009.65 Kelvin. Okay. So and T04 is, what is T04? Yeah, T04 is 543.76 Kelvin. So instead of raising the temperature from 543.76 Kelvin to all the way up to 1830 Kelvin, we used exhaust gas heat to raise it to 1109 Kelvin, which is a big difference, like 500 Kelvin difference we have heated only due to exhaust gas, and then remaining we heated with the fuel. So in this way, this actually reduces our fuel consumption. Okay. All right. So let's go forward. I hope everything is clear as of now. So the high pressure turbine exit temperature we know. Now high pressure turbines exit pressure that we can find using isentropic efficiency. So this formulas we have done several times. Only thing is we need to substitute these numbers properly, and you will end up having expansion from 14.9 bar to 8.38 bar. Okay, or 838.65 kilopascal. All right. The next component that we have is LP turbine. Uh, in the LP turbine, uh, the LP turbine is used to run fan and low pressure compressor. This formula also we already used it, and we found out the exit T07, right? Uh, so if you substitute again, you will end up having T07 to be 1091.87 Kelvin. Okay, and now we need to find the pressure, at the exit of the low pressure turbine. So that will be around 12 125.79 kilopascal. Okay, now this pressure, it is with this pressure and temperature, it actually goes through the regenerator. So please don't forget that this P07 and T07 goes to the regenerator, heats the incoming hot gas from the high pressure compressor exit, and then it comes to the nozzle. So there is a pressure loss from P07 to before it enters the nozzle. Okay, so that is something we should not forget to uh, calculate. Okay. So it goes to the regenerator from the LP turbine exhaust. So the exit pressure will be 2% less. So 98% of P07 will be there. And you will have the exit pressure of the exhaust gas from the regenerator would be 123.28 kilopascal. Now, we also need to find T08. We haven't found that yet. Again, we can use effectiveness formula, but you have to be little careful because m dot is also there, Cp is also there, so you should be careful. Or you can simply use energy balance. So whatever energy lost by the or whatever energy gained by the incoming incoming cold gas from the high pressure compressor exit is the amount of energy given, is the amount of energy lost by the turbine exhaust. So again, if you substitute these numbers, the equations are same. There is no change in the equations, just the numbers are different because of different flight conditions. So the temperature at the exit of the regenerator will be 696.95 kilopascal. So you can see that um, from 1091 Kelvin, it reduces to 696 Kelvin. Okay, while increasing the cold stream from 543 Kelvin to 1009 Kelvin. Okay, so you should just try to understand these numbers. Okay, the next component that we have is core nozzle. Now we know how to do it. We are experts in this. So what we have is first we need to find the choking condition, and for choking condition we'll find the critical pressure. Here it turns out to be 65.47 kilopascal. Since it's a flight condition, we are good because V infinity is less than the 65.47 kilopascal, which means nozzle is choked. However, in the ground condition it was not, because it was not enough. Ground condition the pressure is 1 bar, so that is higher. So here the nozzle is choked and the exit pressure is 65.47 kilopascal. Then if the nozzle is choked, the equation becomes simpler, and you can find from the isentropic flow relations with Mach number equal to 1, you can find the static temperature at the exit of the nozzle, and that would be around 606.04 Kelvin. So that is once you find the temperature, you can find the velocity. The velocity will be equal to sonic speed, because the nozzle is choked and Mach number equal to 1 at the exit. So if you substitute these numbers, you will end up having velocity to be 475.51 meters per second. This is in the cone nozzle. Now we also need to do for the bypass flow. In the bypass flow, the bypass stream has got heated from T02A to T010. Okay, so from I think around 248 to 280 Kelvin to 293.6 Kelvin, right? Now again the same usual procedure. We'll find the choking condition, and from there we'll find the critical pressure, which is 26.53 kilopascal, which is still higher than the ambient pressure, which was 24.73 kilopascal, and hence the nozzle is choked and the exit pressure would be 26.53 kilopascal. So I think here it is not P12, it is P11. There is some typo, so I will change that. Okay. Now we can find the temperature and velocity, which is again, this is chalk nozzle, so we know everything about it. The temperature would be 2244.67 Kelvin, and similarly the exit velocity of the fan nozzle will be again Mach 1, and that will be around 313.54 meters per second. Okay, so you can see that velocities compared to ground conditions are higher, so you might be in the assumption that our thrust also will be higher, so but be careful. Okay, so we are going to see what happens. All right, so next is to find area of the nozzle. So for the core flow, what we have is at the nozzle we have m dot of core plus mass of fuel that we added in the combustion chamber, and hence m dot core into 1 plus f equal to rho 9 a9 and v9. You can use ideal gas relations to express density, and if you substitute these numbers, you will end up having a to be 0.211 meter square. Okay, so our velocity is high, so that's why area is a little bit less. All right, so now similarly we can find for bypass flow. You have your station numbering is 11, rho 11, A11, V11 is your mass flow rate of the bypass stream, and you can substitute these numbers also, and you will end up having area to be 1.913 meters square. Okay, all right, and then what we need to find is the first performance parameter, which is thrust. So the thrust will be both from fan bypass stream and also from the core stream, whose formula we are very confident of. So you can substitute these numbers, and then you can check for yourself that thrust is around 53.83 kilonewton. Okay, since the aircraft is flying, you also have V infinity. Here the V infinity is 237.9 meters per second. So that corresponds to Mach number 0.8. So you can do this calculation. So for Mach number 0.8, the velocity with which engine flies is 237.9 meters per second. So if you substitute that numbers also here, you will end up having thrust to be 53.832 kilonewton. Okay, and the next performance parameter that we have is TSFC. The TSFC, if you calculate, it comes around 17.8 grams per kilonewtons per second. Okay, so this is the TSFC that we got for this engine at flight condition. Next is you have propulsive efficiency. The propulsive efficiency, we are again familiar of this formula. It's the thrust power divided by total thrust power plus change in the or you can say total change in the kinetic energy, or that is also equivalent to thrust power plus kinetic energy lost in both the streams, core stream and bypass stream. And if you substitute appropriate numbers over here, you will end up having propulsive efficiency of 84.3%. And thermal efficiency, we know the total change in the kinetic energy of the air streams divided by the uh, heat input to the system. Okay, and if you substitute these numbers, you will end up having thermal efficiency of 34.91 percentage, and the overall efficiency will be around like 29.43 percentage. So you should be a bit careful. You should not directly compare the thermal efficiency at the ground condition to the flight condition, because it doesn't really make sense. The engine is same. What you should do is you should do the same calculation for uh, without intercooling and regeneration, and you should compare its efficiencies. So the reason to use intercooler and regenerator is to improve the efficiency of the engine. So now we are getting 34.91 percentage. If you do a two spool gear turbofan engine for you know um, without intercooler and regenerator for the same engine, then you will be able to see a different thermal efficiency, and you can compare those two values. Okay. All right. So here I have just tabulated the all the parameters that we calculated from this for the flight condition. So we saw the efficiency is around 34.91 percentage. Okay, and also thrust is 53.832 kilonewton. TSFC is 17.8 grams per kilonewton second. Okay, there is an increase in the fly exit velocities of both core stream and the bypass stream. Uh, from ground condition to flight condition. Those are some observations that you can see here. Okay. So I hope this turbofan engine with intercooler and regenerator for flight conditions would be this numerical would be really helpful for you. Although it may not be helpful in terms of assignments that you're going to solve for week 9, but in general it would have given you some confidence and some bit understanding of these concepts. If you have any questions, you can ask me. Next week, what we are going to do is we are going to. So next week is totally about turboprop engine. Uh, you must have got week 10 contents turboprop engine, and you should be familiar with this diagram. So this diagram contains, it's like a summarization of week 9. You know, uh, contents, you can say, brief summarization. So uh, next week what we are going to do is we are going to see turboprop engines, and especially in turboprop engines, what we will solve in the lectures will be single shaft turboprop engine, and also twin shaft turboprop engines. um, so what we will do is we will try to solve the same intercooling and regeneration with the turboprop engines, okay, which we actually would not have touched much in the lectures, but we will see how the performance is when we have intercooler and regenerator in a turboprop engine. Okay, so that is the agenda for next week. All right. So if you have any questions, you can stay back and ask. Also, if you have any questions, if you don't have questions now, uh, you can go revisit and come back next week, and also you can ask some questions if you have any doubts. Okay. All right. Thanks for attending. So feel free to stay back and ask your questions. If not, we will meet next week. Thank you, Tushar and Krishna Kumar. Tushar, I hope your doubt is clear about the exam. I'm not sure about the exact exam date. Did you receive the exact exam date? Probably your mic is in mute. Okay, 26 October. All right, I think Tushar left. Probably there was some problems with his device. So, yeah, the exam is on 26th October. So you don't have exam on 26th September. Okay. So I hope that should clear your problem.